Okay, welcome everyone to the second week. So registration is during the coffee break. So people that are doing the registration today that were not here last week, please be sure to be here on time for the next talk, because then I'll make the logistic announcements and so on after you registered, and so that we don't get late with the first talk. And so it's a pleasure to have Balt kick the first week with kick out the first week with some theorems for the lightcone Bootstrap.
Thanks, Pedro. I think it's the second week, but that's just. This talk is being recorded, which is why I'm talking into this microphone. And also, if you have a question, it would be great if you could use the microphone. So there are a couple here; they should be passed around. So today I'd like to talk a bit about some rigorous and precise statements, hence theorems, that I obtained together with Friedrich and Jashin in the context of the lightcone and the modular bootstrap. So to illustrate what we did, I think it is best if I just start with a very easy start and actually use throughout the talk a very easy toy example where I consider a 4-point function of identical operators in a CFT. And I'm going to look at this 4-point function. Of course, we can decompose it in conformal blocks, but I'm going to decompose it just in terms of monomials, z to the power hk, z bar to the power h bar k, then some coefficients ck, which are positive, and some sum over k. Right, so of course we know a lot about this thing. We know in particular that there's also a conformal block decomposition with positive coefficients. We know about the convergence, we know various other properties. And the main property I'd like to talk about is the behavior as z bar goes to 1. Which is of course dominated by the identity in the cross channel. So that will be something of this form. Delta phi times 1 plus, and then corrections. And corrections are going to be small by assumption. 1 minus z bar to the power h min, or h bar min, so h bar min in the T channel, but it's a crossing symmetric guy. So, and of course I'm going to assume that h bar min is strictly positive, so there is a twist gap. Otherwise I have nothing to say. So this is my starting point, this equation, let me call it star. And the obvious question you can ask, and that many people have already asked, what are the implications of this equation star for the left-hand side, the OPE data, or let me call it, I'll use the word, the symbol S, and I'll probably confuse you and say spectrum, but it's really the spectrum and the OPE coefficients. So it's really this set of triplets for all k. Right? So that's the question I'd like to answer. And of course, there's a simple and naive answer that gives you a good indication of what is actually true or what is actually provable. So let's very briefly consider the naive answer, which is just, well, there are two steps in the naive reasoning. First of all, if I send z bar to 1, then the terms with large h bar are less and less suppressed. So in that sense, z bar to 1 is probably related to h bar to infinity. And the second statement will be that this left-hand side has a simple monomial decomposition. So this z bar over 1 minus z bar delta phi just decomposes in itself into some double sum z to the power delta phi plus m z bar to the power delta phi plus n, and with some coefficients that are really not important, they're Pochhammers divided by factorials. Okay? So then you say, well, look, let's combine these two statements and say that for large h bar, the spectrum is going to, so we say for the spectrum, or this S, this set of OPE data, for large h bar in some way is going to approximate this spectrum or the set OPE data that I extract from this guy, which I'm going to call the GFF OPE density. Right, so that's your intuitive result, and as we'll see, it's not completely wrong, but it is definitely imprecise. I draw some squiggly arrow. In the literature, you can find tildes, you can find squiggly arrows, you can find straight arrows, you can find equal signs with footnotes, and so on and so on. So we'll try to make this this a little bit more precise. So let's see, for example, a little bit of what you would naively expect to be true and what this squiggly arrow could possibly imply. So here the spectrum lives on a grid, and conveniently there's already a grid here. So I'm going to plot vertically h, and horizontally, well, I could plot h bar, of course, but it's easier to plot h bar minus h, which is just a spin j, because that is an integer both on the right-hand side and on the left-hand side. And if you work with monomials, it's an arbitrary integer. So you have spins, 0, 1, 2, and so on. And you have the spectrum for the right-hand side. It starts with delta phi, then delta phi plus 1, delta phi plus 2, and so on. And the spectrum of the right-hand side, of course, lies on the intersection points of this grid. So for our left-hand side, well, we don't really know. For spin 0, there's the identity, but that's not part of the sum. And then there are a couple of other guys. Spin 1, we also don't really know. But eventually, we expect things to converge closer and closer to these grid points, right? So that's the expectation. But you can ask, well, in which sense is this true? This may just be true in some average sense. And if you say the word average, well, you can ask, well, in what kind of sense do I have to average? So, for example, for this second trajectory here, I can draw something that's such that this is only true in the average sense. I can, for example, admit oscillations in j, so that if I for each individual j, this limit is not true, but if I average over spins, then on the average I get the right answer. So that's one possibility, and so far it's nothing excludes this possibility. Another possibility is that maybe there's something wrong. Here I'm plotting the spectrum. Maybe there's something wrong with the OPE coefficients, right? Or maybe, for example, there's an OPE coefficient here that is 0. An operator or monomial is just missing, and then it goes on. There are a couple maybe with the higher coefficients, and then there's a 0 again, and then higher coefficient, then 0 again, and maybe there's an infinite sequence of zeros. So that could be the case, and that of course would be would require some kind of averaging also in spin, or maybe averaging in the h direction. Sorry, I should say this kind of thing you can cure by averaging over spin, and this kind of thing you can cure by averaging over twist, but also over spin. So it's clear that I think this statement is a little bit imprecise, and it would be interesting to ask what happens exactly. Okay. Any questions? Anyone still awake? Yes, some of you. Thank you. What about degeneracies? By definition, they're absent. So let me say they're. I cannot say anything if the same monomial appears twice. Then I can't say. You have to press the button for a bit long.
Can you say if there will be some degeneracies in the limit when h bar goes to infinity? Will you be able to distinguish, or it will be averaged?
I think it'll. I mean, I understand what you mean, but it's basically saying that if the same monomial appears twice, and obviously right, but that I cannot distinguish that. Yeah, I just fuse it back into one monomial. Okay. So that's the question I'd like to address, and we'll prove a little mini theorem related to this question that'll make this question precise. So before doing that, let me briefly spend a few minutes on the why question. Why am I doing this? Why am I interested in this? And in doing so, let me first address a kind of criticism that I've heard from friends who are still friends, but they say, well, are you not just proving rigorously what everybody knows to be true already? To which I would say that what everybody knows to be true already depends, I think, quite a bit on what you ask, on who you ask. I mean, this is an imprecise statement, and the footnotes in there are also imprecise. So the very act of trying to make this precise is already interesting. So it's not just making things rigorous, but it's also just formulating a precise statement. That I think is interesting by itself. Okay, so that is my answer to this this criticism. And in particular, it would be so you can make this increasingly precise, right? So you can say, what kind of window do I have to average over in H space, in J space? Can I make it small? Can I make the H window smaller and smaller as J increases? Can I say something about finite spin? Right, there are all kinds of variations of this imprecise statement that are interesting, and that one would like to perhaps prove. So let me stress in particular the finite spin case, because if you can prove something for finite spin, that would be nice, because it may tie into the numerical bootstrap, of course. And Ning Su, who's here, already wrote one paper where he assumed some parts about the lightcone bootstrap to improve convergence of the numerical bootstrap. So that is one motivation to make precise and understand precisely what people mean with this squiggly arrow. The other is that there are various other formulas and structures in that are used to analyze CFT correlation functions. Most importantly, or at least historically, is of course the Lorentzian inversion formula. But there are many others. I mean, the conformal dispersion relation is one. You have these dispersive functionals. You have Mellin space. You have the proof by Tom and collaborators of the ANAC, and so on. And all of these are at the physical level of rigor quite convincing, but there are some open questions regarding their statement as mathematical theorems. And this is kind of what motivated me to revisit this whole lightcone bootstrap thing. So that's why I mention it. I'm not sure the results I'll prove will directly be useful here, but at least it was a motivation. And in particular, one question is that to prove these at the moment, we need some good behavior. We need in a particular limit of the correlation function, which I call the lightcone limit on the second sheet. I'm not going to talk about what this means, but it's really some particular strange limit of the correlation function, and in that limit the whole correlator needs to be nice. It's not so easy to see from this decomposition because you go on to secondary sheets, but we need that limit to be nice to prove various things in CFT. So it would be nice to understand this and see if we can actually say something about this lightcone limit on the second sheet. One particular application that I had in mind, which was my really my original starting point, was this idea of QFT and EDS and its flat space limit. Flat space limit. So here I have in mind, I put a QFT and ADS. On the boundary I have these correlation functions, these conformal correlation functions. Let's call them solutions to the crossing equations. And I have that for every value of the ADS radius. And I make my ADS flatter and flatter and flatter. So I have this family for each value. And as ADS becomes flat, there are these ideas that this correlation function should just become a scattering amplitude of the QFT. In which way and under which conditions, we don't really know at the moment. But it's an interesting observation because it allows me to prove things about scattering amplitude, starting not from the LSZ prescription and the Weidmann axioms, but instead just from the CFT axioms. Here I have analytic functions. The CFT axioms, I think, are super clear for these kind of 4-point functions in particular. And it would be very nice to prove, for example, some property of scattering amplitudes, let's say the Frossard bound. So would I be able to prove them, the Frossard bound from the CFT axioms? I think that's very nice, and that would be a nice result. And this is my longer term, one of my longer term research goals. So you see that this is just a microscopic step in some sense, maybe not even in the right direction towards this goal. Okay. So that was my the motivation bit.
So to prove Froissart bound, you will need to assume something about the relation of CFT axioms to the scattering amplitudes. Are you going to assume it as another axiom?
I can say that this, yes, kind of. I can say that the scattering amplitudes that I get from the flat space limit in Q of Q, well, I might be able to say those scattering amplitudes that are obtainable from the flat space limit of a Q of T in ADS, in a particular way that I'm going to define for you, all of those will obey the Froissart bound. So that will be the statement I'd like to push. Thanks. Yeah, Miguel. I can also repeat the question if it's... Oh, okay, the mic is coming. You should switch it on though.
Okay, good. Yeah, I was wondering about polynomial boundedness, which is an assumption which is like the most uncomfortable one in the S matrix. Like, do you think you can get that from the CFT?
Yeah.
How?
That's a different talk.
Okay.
But it's sort of the fact that the conformal dispersion relation only needs one or two subtractions, provided we can control this lightcone limit on the second sheet.
Okay. Okay.
Or maybe even without controlling it. We already control it a little bit, right? So it's the statement that you find in the literature that with two subtractions you should have, things should be fine.
Okay.
Okay, that was the why. Let's go back to our equation and try to prove some stuff, and I'll pull some theorems out of a hat, so I'll try to reserve this blackboard for the theorems that I'm going to use to step by step go from this equation that I called star to something rigorous about the spectrum. And so it's going to be a 3-step thing, and I think I'll spend, well, slightly less than 10 minutes per step, just because I want to give you a little bit of context as to what is going on. So the final result will be there towards the end of the talk, but not very quickly. So the first step will be to employ a so-called Tauberian theorem. So most of you know what this is, definitely the more senior people, but let me very quickly review the statement of Tauberian theorems. So the simplest, I'm really just going to do this at an first year undergrad level. Of course, you all know the geometric series, but there's a more general statement. And there's also a theorem. So this is the simplest Tauberian theorem that I could imagine, which says that if you modify the coefficients in the sum a little bit, but you still suppose that as x goes to 1, this behaves as 1 over 1 minus x, then the coefficients asymptotically also behave like 1 in some average sense. So the coefficients dk go to 1, but only in the sense if I average from k equals 0 to some large lambda. So this, of course, is just the same as lambda. And this statement is true as lambda goes to infinity. So that's the very simplest of Tauberian theorems. And there are many, many generalizations of these Tauberian theorems, right? You can assume different behavior here. Well, so let me write that first of all. There are many variations. You can assume power law behavior, you can assume exponential behavior, you can maybe say that this behavior is true not just in as x goes to 1 along the real axis, but along the complex, maybe everywhere in the complex plane, along any direction. Maybe you can try to account for subleading theorems and so on and so on. So there's one caveat here, which I forgot to write, which is that if this is only true if the coefficients are bounded from below, let's say positive. But that's fine for us because we're working with unitary CFTs, so our coefficients are positive. Here I should also stress that I'm using this notation, I will use it throughout the talk, that A tilde B as C goes to D is actually a rigorous statement. It just means the limit as C goes to D of A over B equals 1. Okay. So if you just assume this, it's clear that this theorem, the averaging over K is needed. You need the sum over K to lambda. A simple example that shows this is sum over K x to the power 2K, where the coefficients are 2, 0, 2, 0, 2, 0, but it's an elementary exercise to show that the x to 1 behavior is exactly the same as is exactly of this form. So this shows that you cannot just throw away the averaging. Okay, so this is Tauberian theorems. This is Tauberian theorem. The Tauberian theorems entered the world of the conformal bootstrap first in 2012 in a paper by Slava and 3 collaborators. And since then it's been used. They've been used in several cases in the conformal bootstrap. So I'm not the first one to introduce these theorems to the bootstrap community. But as I said, there are many variations. There are many textbooks written about these things. So you can just find the Tauberian theorem that suits your case the best. So the particular version of the Tauberian theorem that I'd like to start with is, of course, this one, where I'm going to trade the z bar variable for a lambda. So I'm just going to say that this thing, as z bar goes to 1, suppose that it behaves like 1 over 1 minus z bar to the power delta phi. And of course, let me say again, the coefficients are non-negative. Then this implies that if you sum over k, these dk, well, I have two differences. I have arbitrary powers and I have a more general power here, but it's all easy to take into account. You just truncate this sum. So you only select the terms where h bar k is less than lambda. Then asymptotically, as lambda goes to infinity, that behaves exactly as if I were summing the coefficients of the expansion on the right-hand side. Well, that we've already seen. So k to lambda. Those are just the Polhammer symbols again, divided by the factorials. And I'm only interested really in the lambda to infinity behavior. So this is just, as lambda goes to infinity, lambda to the delta phi, as it happens, divided by gamma to the delta phi plus 1. Okay, so this is the Tauberian theorem. And the Tauberian theorem is useful for us because we are going to use it to eliminate z bar in favor of a lambda. So I basically now have to apologize because I have to basically copy the statement of the Tauberian theorem for our case. So let me try to at least write quickly. One sec. So our equation star with the Tauberian theorem implies that sum over k, ck, z to the power hk, truncated to h bar k less than lambda, as lambda goes to infinity, behaves like there's this prefactor lambda to the power delta phi, gamma of delta phi plus 1. And then, of course, we have the z dependence still, and that'll just be z over 1 minus z to the power delta phi. Right? So you see I have basically truncated this sum up to some large lambda. But we see a divergence with lambda on the right-hand side. So this divergence should come from the tail of the sum with the terms with very large lambda. And in the h direction, we also still have suppression just because z is between 0 and 1. So now you can ask where and how is this equation valid? For which values of z is this equation valid? Well, clearly the analog of this dk here is just ck z to the hk, so I want this to be in particular positive. I also want the whole thing to converge, and I want the t-channel expansion to converge because I need this to be true. So this is true for any z between 0 and 1 strictly.
Sorry, is this the correct truncation? So you're truncating an HK bar, but then you insisted that horizontal axis is not H bar on your
Sorry, if
on your picture on the left board,
yeah,
on the left board.
Left.
Yes.
Leftmost.
The picture. So
yes.
to the right. Yes, this one. So you insisted that the horizontal axis is not H bar, it's J.
Yes.
And then.
Thanks. It's the same thing, right? Because I'm always looking at the limits H bar. Yeah, it's true that this picture at the moment is imprecise because for large H there's a significant difference between H bar and J. But we'll fix that in a moment. Okay. So the picture is not correct, but I think the equation is correct.
Okay.
Thanks. So this is true for Z between 0 and 1, where I have all the properties that I require for the theorem to apply pointwise. So for every Z, you give me a Z, the theorem is true. You give me another Z, the theorem is true. Right? But I'm not saying anything about uniform convergence or, right, there's a limit understood here. I'm not saying how fast the limit is. How fast this limit is, this equality holds, that depends on the particular value of Z. In particular, if you change Z to 0, it's going to be slower and slower and slower. So the hard question of the lightcone bootstrap, if you already know Tauberian theorems, which we know for 13 years now as bootstrappers, and Slava a little longer, and mathematicians a lot longer, is how to eliminate Z. Right? That's the hard part. I mean, you cannot just expand around Z equals 0 because this equation is true pointwise, and pointwise limits and expansions don't commute, and in particular in this case the Z to 0, like I said, the limit, the approach to the asymptotic value becomes worse and worse as Z goes to, as you take Z to 0. You also cannot just take Z to 1, because then you lose information. We want finite twist. We don't want to do the Euclidean bootstrap that that Bauer and Sasha did, where you take H and H bar large. Then you can just take Z to 1 and apply fancy Tauberian theorems in that region. But we cannot do that because we want to sort of get rid of Z in favor of H and keep H finite. So we need a new ingredient, right? That's the main lesson here. Okay. Any more questions? Okay, so we're done with the Tauberian theorems. We can move on to the next theorem and next step. So this is going to be step 2, which is a theorem in complex analysis. It's part of a general class of theorems. So it's called Vitali's theorem, or Vitali's theorem. I think there's an S there typically. Of course, it's named like anything in mathematics and a lot of physics. It's named after the wrong person because I think the theorem was first proved by a guy called Porter. So in some literature, you'll find it as the Vitali-Porter theorem. But my standpoint is that anything is named after the wrong person anyway. So we should not try to be super precise. So it's part of this general class of theorems where you have some sequence of functions which are analytic on some domain of the complex plane for each value of n. And you ask what happens in the limit, right? You ask what kind of statements I can prove about these kind of families of analytic function. So the theorem that I want to highlight, I mean, this is really not the right theorem to start with if you're teaching this subject properly. Then you should start with Montel's theorem. But I'm not teaching it properly, I'm just giving you an overview. So we'll just say Vitali's theorem, and actually I'll just give you the baby version there's a slightly stronger statement you can find. But it's easy to find online. So suppose you have a limit, at least in some subset. So I'm going to assume that it holds pointwise on some subset S, which is a subset of D. Okay, I didn't say what this subset is, right? It could be a point, it could be an open set, and so on. But the natural questions to ask are, is the limiting function analytic? Let me erase a bit more. Right? What kind of control do I need for this limiting function to be analytic? And if it's analytic on S, can I then analytically continue to outside of S so that the limit and the analytic continuation commute? Now the answer to both of these questions without further assumptions turns out to be no. It's easy to find counterexamples. The limit does not need to be analytic, and the analytic continuation and the limit do not need to commute. That's your homework exercise if you want. It's very easy to find some examples. So we need one more, we need a bit more, we need some more assumptions. And what Vitali said is that basically you only need boundedness to prove a lot more. So the supremum Z in D for any n, so the supremum of the functional, so the family, every element of the family is bounded, is what I'm saying here. Is what I want to say, and that's what I'm saying here now, right? Every element is globally bounded. Actually, you can assume it's locally bounded, the theorem still works. But if if it's globally bounded, like so, then you have a lot of results. You have that f of z is analytic. On D, you have that f of z, the limit as n goes to infinity of fn of z exists, and it just equals f of z, which with slight abuse of notation, I call the analytic continuation of f of z in S to all of D. And convergence is uniform, or almost uniform. Some mathematicians write UCC, uniform convergence on compact subsets. So it's not globally uniform, but in any compact subset, it's uniform. Yes, thanks. That is another thing I forgot. I wanted to write now. For sufficiently large, I don't want to write the exact thing for some sufficiently large S. If S is a point, you clearly can find all kinds of counterexamples. But if S, technically speaking, it only needs to have an accumulation point in D, and that follows because the zeros of an analytic functions are isolated. And then that should be the hint in proving the theorem. So you need S to contain at least yes, an accumulation point, so it contains definitely infinitely many points. But S does not need to be open. So that's good. That's good for us. I hope you see where this is going, because we have our complex Z plane. We have the unit disk in which we're working, because we're working with monomials anyway.
Balt,
Yes.
don't you want to just give one simple counterexample, just so we see a little bit what we should be afraid of?
Yeah. Good. I was debating with myself whether I should. You take the limit z to the n as a sequence. That of course goes to, as n goes to infinity, that goes to 0 inside the unit disk, or it goes to infinity outside the unit disk. So this is the simplest example that shows that analytic continuations and limits do not commute. Because inside the unit disk, I get 0, I continue it outside, and that is not at all, 0 is not at all the same as infinity.
Which one failed of the assumptions? It's bounded, right?
It's not bounded outside the unit disk if z is bigger than 1, right? I mean, I can do this along the real axis even. If
But I thought I just needed D. D could be the disk, right?
Then inside the disk, I'm fine.
Ah.
I never go outside. Yeah. There's another beautiful example where you take some.
But if it's a disk of size 2,
Then it's not bounded because it's like 2 to the n at the end. 1.99 at the end. There's another example which you can try to build a step function in the theta plane. in the z-plane, sorry, a theta function in the z-plane. So let's take a compact set and call it 0 here and 1 here and maybe 1 also at the boundary. That's a function. It's not analytic, clearly. And you can try to approximate this. You can try to cook up a series of analytic functions. And if you know Runge's theorem, it's very easy. You cook up a sequence implicitly of analytic functions that converges to this step function, pointwise for every z, including the imaginary axis. It just converges to 1. But, right, Vitali's theorem says that this is weird, right? It shouldn't be the case, or at least not if it's bounded. And so what Vitali's theorem really says is that if you take any open subset here, then they're going to be arbitrarily big oscillations, that it's going to be unbounded, such that this sequence is going to be unbounded. That's a direct implication of Vitali's theorem. So it's a complex analog of this Gibbs phenomenon, where you Fourier decompose a step function, right? And you get these kind of oscillations. There, in the Gibbs phenomenon, it's kind of bounded and under control, and here you can, Vitali's theorem basically says, no, there's no way you can, these fluctuations close to the threshold are going to remain bounded. Thanks. I hope this counts towards my question time, because I crossed it out from my talk because I thought it would take too much time. Any other questions? A uniform convergence on compact subsets is UCC. That was the question. So you see, we have, let's go back to our statement. We have Z between 0 and 1. That's where this thing works pointwise, but you see, we can extend this now to any region where it remains bounded. So, because this S is definitely sufficiently large, this unit interval. And so, in particular, we can, of course, add an arbitrary phase. Where am I? I'm too fast. We add an arbitrary phase. We can set Z equals R e to the I theta. And then, of course, we know that this sum, CK, K, you know what I mean, right? CK R to the power HK e to the I theta HK is less than or equal to the same thing with theta equals 0 e to the I 0 HK. And this has a limit, so it's definitely bounded. So at least for sufficiently large lambda, right? So everything is fine. I can now add an arbitrary phase, and the theorem still works. In fact, we now have a stronger results that it's uniform on compact subsets. So we can add this phase and put ourselves here, and the theorem will still be true. This same statement will be true also. So it's not just here pointwise, it's a much more general statement. So I can write this by Vitali's theorem. We'll have exactly the same statement for Z equals R e to the I theta, where R is between 0 and 1, but theta can be arbitrary.
Balt, so you are making a very important contribution to our field. You are bringing this very important theorem, just like we brought Tauberian theorem a while ago. So I think it's very important that you stick to the right pronunciation of the name, because otherwise all the Italians in the audience cringe.
Sorry, yes.
It's supposed to be Vitali's theorem, for God's sake, so let's just stick to this.
Merci. Vitali was Italian, so yes, Vitali's theorem. Thank you. I should say Vitali, and so by Vitali, I can add a phase, and I wrote theta in R, right? That's the fun part, because I continue, and then I hit the second sheet, and I can continue and continue, and maybe even on a third sheet, and the theorem will still be true at this point. Which is surprising, right? I mean, I was very surprised because you do something, you have a result that follows from the T-channel OPE, and you're pretty far from convergence of the T-channel OPE here. But the theorem still holds because of Vitali's theorem. It's basically, right, this is an analytic function on this multi-sheeted cover of the plane, and there's no way that, right, analytic function, it basically follows the limit that you have on the subsets or a divergence. There's nothing else that analytic functions can do. And if it does not diverge, then it follows what happens on the subset. So that's nice. We have a much stronger result. Let me write it in a bit more detail because I'm going to need it a bit more detail for the next and last step, which is that, so I have the same sum, same as before, that I'm not going to change, r to the power hk e to the I theta hk as lambda goes to infinity behaves like lambda to the delta phi gamma. I hope there are any markers left that are good. Delta phi plus 1 r to the delta phi e to the I theta delta phi 1 minus r e to the I theta to the delta phi. Okay? So this is of course what I mean with the analytic continuation. And then I can erase this. So I just write that this is true. Okay,
But
so
is there still time for questions? Because is there like what can you say about the rate of convergence? So that's uniform on compact sets.
Yeah.
Is there anything interesting that can be said about the rate of convergence?
I think it's uniform on compact subsets, right? So I think I don't know any the rate. So the compact subset like this works.
No, but for example, do you if you know something about?
No, I right. It will depend, of course. If you take your subset, your operator very close to 0, things will be bad. But that is not 0 is not included in any compact set in this region. So I don't know. I have not. It would be nice, but I have not. Since I don't have I did not bother to estimate the subleading terms here. I can't say at the moment anything about the subleading terms here.
But if you knew subleading terms there, would you say something here? Like is there some Vitali's theorem?
Probably you'll be able to do something. Okay, let me not say that. You're asking basically if I know the convergence rate at this thing over here, do I know the convergence rate over here? Yeah. That actually does seem hard given the how simple the proof of Vitali's theorem is. Because right, it's just a bit of an abstract proof. It doesn't really give you a lot of control.
But please turn on the mic, yeah.
Do you have a mic? The mic is coming.
I'm sorry, I have to make some noise first before I get the mic. I was asking, isn't the tail at any value of theta bounded by the tail at 0 value of theta?
But on the secondary,
Just by
I'm not sure because I don't have positive coefficients after I subtract the T-channel identity. I think I'm sorry, I'm not very fast. So I guess
if you sum over, if you keep only the terms at like large HK or whatever. Then isn't like you just bound it at like the same bound that you have on the right board, but for a subset of terms?
Yeah, I think we should talk afterwards because I'm not fast enough to parse what you're saying. But right, for subleading terms in general, the problem is with this statement because the CK are not positive.
Okay.
But sorry if I don't understand. Okay, so who has a good idea as to what we can do next? How do we eliminate Z in favor of theta? Or is Z, sorry, in favor of H? It's very easy, right? This is just a Fourier decomposition. So you just inverse Fourier transform. You have this for all theta. So we can just take a Fourier transform now, no? So let me write something that is not quite true. Or, well, I'll just not write I'll write a question mark. It should be clear. So we'll take the inverse Fourier transform. We'll just write the d theta over 2 pi of this whole gadget. And I need some space to correct what I'm going to say later. E to the I theta h over R to the h. Great, that'll give me a delta function, and this will just give me the spectrum. Sum over k, ck, delta h minus hk. So it'll give me a spectral density. Right, and on the right-hand side, we'll get the same thing. So we can do the same thing. So this is the question mark. We're not quite sure if this is true yet. And the right-hand side is very easy again, because it'll be the OPE density of this thing, which we've seen various times. It's just this this Pochhammers again, right? So you get this factor, and then sum over m, the Pochhammers, delta phi m divided by m factorial, delta function h minus delta phi minus m. Right. So now you say, okay, this should almost be true, right? I mean, I know this to be true for all theta, this statement, and I'm just integrating now over theta. But of course, as I repeatedly say at various conferences, limits and integrals don't commute necessarily, right? If this has some bump in the theta variable, and this, so suppose, right, you're integrating over theta, and suppose this is something else, this is some bump function in theta. Then and then in the limit, as you send this bump function off to infinity. Well, the integral will always fill the bump function, so the integral will always be non-zero, but pointwise, the limit will be 0. So that shows that even, and you can even make it uniform on compact subsets. And the limit, and that shows that limits and integrals don't commute. So we cannot quite infer this statement because we have the lambda to infinity statement for the integrand, but we want to put it outside and have it for the integral. And that's not automatically allowed.
So you said that you could go to the second sheet, but now you're not using the second sheet anymore?
Oh yes, I'm integrating over theta from minus infinity to infinity. So I'm using all the sheets.
Okay.
Thanks, sorry. I should have written the bounds. Yeah. Right, so we need a little variation of this statement for it to be true. And of course, the little variation is just, well, I'm just going to insert some other function here, dh, some function phi of h, and then do the theta integral. Right, this is my test function. If phi would be a delta function centered at some particular point, then I would just pick up this thing again and go back to where I start. But phi in general is not the delta function centered at a point, and for any finite lambda, I can just take it outside the integral and see that this delta, so then I have the delta functions that are produced from the theta integral, and I see that this delta should just become a phi. So this is true for any finite lambda, and here h bar k, right? Our sum is still truncated, of course. And on the right-hand side, the same thing will happen for any finite lambda. This delta function is just phi evaluated at the delta function. Okay? But if I want to take the lambda, so this is for any finite lambda, I take this integral outside, and I see exactly, I think it's obvious that you replace this delta with a phi. But for the lambda to infinity limit, I keep this thing inside. And this is basically the Fourier transform up to this factor r to the h, but it's the Fourier transform of my test function. And if this thing is bounded and integrable, then I can use a thing called the dominated convergence theorem, and I can swap the limits and the integrals. So this is actually true if phi obeys a very simple condition that its Fourier transform is L1. So I just have to say that the integral d theta 2 pi phi of h e to the minus I theta h r to the h also dh, and this thing in absolute value, right? This is going to soften for me the theta integral. So I want this guy, if this guy in here in absolute value is integrable, then I am allowed to use the dominated convergence theorem. Right, so this tells me this is the class of test function. This is the averaging over H that I need. I need to average over H with test functions of which obey this property, and then I have a mathematically vigorous result. If I do any test function for which this property is not true, I'm not allowed to cross out this question mark.
Where did the fact that the convergence was uniform on compact subset compact, where did this compact go?
It did not enter. It could have been pointwise. Sorry, the question was whether where the UCC went. I think in this case it did not enter.
But what entered then?
Pointwise. Pointwise for any theta and real theta.
Oh, okay.
That's where I needed Vitali's theorem. But pointwise suffices to use the dominated convergence theorem, I think. Right? Any people? There are probably many people who know this. So phi cannot quite be a delta function, so let me say what kind of phis we can use. Right, we cannot probe the spectrum exactly. Phi cannot be a delta function. In fact, it cannot even be a discrete. Let me switch to blue. I think I have more good blue markers. So I'm going to draw phi as a function of H.
Balt, sorry, can I ask
Yes.
again about the dominated convergence? So in the condition you only put the integral of phi needs to be less than infinity, but I would have expected that for dominated convergence theorem to apply, you would need that the limit lambda going to infinity of the whole integral.
Sorry. Yeah, I did not mention. It was supposed. Yeah, it was assumed, right? Because here, if I insert theta, right, it's true that this guy should not blow up. Absolutely, you're right, and I should have said that. Thanks. But it does not blow up because I just insert phases, so it's never going to be bigger than its value for theta equals 0. Yeah, thanks. Which again had the limit. So the class of test functions that I'm allowed to look at is not of this form. I cannot take phi to be a delta function, so I had red for a cross. This is not allowed, and this is also not allowed. But a little bit of smoothing works, in particular if you take phi to be some nice smooth bump function, maybe centered at some value delta phi plus an integer of some width, compactly supported, say epsilon, 2 epsilon maybe, right? And then afterwards it's 0. These functions are totally fine. And this kind of averaging is totally allowed. And of course, I mean, there's one little strange thing that there's this power r to the h here. Think of r, you can pick it to be whatever you want, like 1/2. So phi of h should also not, right? It should also, at large h, be 0 or decay fast enough to compensate for this divergence. But you're not going to try test functions that blow up at large h. Those give you very little information anyway. So we have a result if we sum over j to some large lambda and integrate over phi over h with some test function phi, maybe compactly supported at each of these intervals. And so we can immediately conclude, right, for these type of test functions, you see I sum over all the operators to some large lambda, I multiply their OP density with their OP coefficients with the phi function at this value. And so I really select only the operators in an arbitrary small window because I can take the epsilon there arbitrarily small. And for any window, no matter how small, I need to reproduce a divergence which is here, the lambda to the delta phi. So I need to get infinity to a first approximation. And so we immediately conclude that there must exist infinitely many terms. So there exist infinitely many terms with h bar going to infinity and h in delta phi plus m minus epsilon delta phi plus m plus epsilon. So that is the theorem that I wanted to prove, or at least the corollary. The theorem is probably this statement, right? This is true for all phi, and the corollary is basically this statement, right? So in the paper, so this of course is true for all epsilon, no matter all epsilon greater than 0 and all m, all integer n. Epsilon can be arbitrarily small. And m also, and m needs to be finite. So this also addresses Peter's criticism that right, lambda, a cutoff in j and a cutoff in h bar are not exactly the same, but you see that I now project onto a finite twist interval, finite interval of h, and then to leading order they're the same. So so this is of course the toy version, because we prove it just for monomials. You should now repeat the whole analysis for conformal blocks. That's what we do in the paper, or what I did in my first paper. And it also, I should mention that it required a new Tauberian theorem for conformal blocks, which was proven a few years ago by Slava and Jashin. So that was extremely useful for the variant with conformal blocks. And another thing I should mention is that the statement, this exact statement for m equals 0 was also already proven, but for the subleading Regge trajectory, it was not known. Yes?
So for conformal blocks, there is, if you just go to the free theory, there is nothing for m greater than 0. So something in this proof must go wrong in the free theory. Can you specify what?
Yeah, I think you asked me this question before. It's in the free theory, so take just the free theory in higher dimensions. So there is a twist gap, even though you have higher spin currents.
Well, the GFF coefficients vanish, right? For
and then Johan says that you only have operators here at the leading twist, and there's nothing here and here. So it's true that this statement for, and Petter is already giving me the answers. So this statement is still true, because the conformal blocks themselves have an expansion for all m. So for monomials, it is still true. So nothing I said in this derivation needs to be wrong. For conformal blocks, it is true that there is this particular solution where there's only one Regge trajectory and nothing else. And then it's indeed not true that this statement as written now does not hold. But what the version I wrote in the paper is basically saying that the spectrum is large h bar when averaged in this particular sense with the test function, right, arbitrarily supported, and summed over j, right, with this averaging, goes to that of GFF, and that is true. Also in your free thing, because for the free theory, the GFF spectrum with that value of delta phi that saturates the unitarity bound has only one Regge trajectory.
Okay, thanks.
Yes, good.
So can I also ask a question?
Yes.
For this, for the Tauberian theorem that you start with, the first line on the middle board, can you use some sort of complex version of it to estimate, how quickly this limit is reached, and then?
Yes. No, we don't need to. We can do even better. So in the last 3 minutes, I want to announce the death of the Tauberian theorem, or the usefulness of Tauberian theorems for the Bootstrap, because we can do better, I think, and we did better, and that's in upcoming work. So the Tauberian theorem, I erased it, but it was this behavior as right. You have your g of x, which is some infinite series, and you have your behavior as x goes to 1. It's something like 1 over 1 minus x to some power, and then you deduce some result about the coefficient. And people have, like I said, there are many variations. You can assume this to be true in any direction in the complex plane, like you were asking. But it's a bit, it's still, this assumption is still much weaker than it only uses very little information of all the things we know about CFT correlators. We know much more. So I can just write the spin J projection, say the OPE density at spin J. What I mean, I'm not writing formulas anymore because I'm basically out of time. Is just an integral d theta. I mean, J is an integer, so I have some compact integral of G where my Z and Z bar depend on theta, like e to the I theta, e to the minus I theta. Right? So to project onto a particular spin, I just need to integrate the correlation function. And then, of course, I know a particular limit, and in that limit, this integral should be dominated. Right? In the J to infinity limit, so there's an e to the I theta J, sorry. In the J to infinity limit, this integral should be dominated by the T-channel identity. And then you can use, that's what the Tauberian theorem uses. But if you want, right, if you want an estimate for theta not in the dominant region, I can give it to you using perhaps the S-channel decomposition or subleading terms in the T-channel or other bounds. So I can just estimate the integrand for any theta, sorry, for any J, and get the result directly for the OPE density at large J. So I can say that the limit as J goes to infinity of this OPE density averaged suitably in H is something. And this is the upcoming work that we are going to, the paper we are going to write, where, so there's a lot less averaging now, basically because we can just estimate these type of integrals very easily, using maybe crossing symmetry twice. And we can get the result for these, I think for this class of test functions, maybe even smoother test functions, where instead of summing over, so we replace this sum by a limit as J goes to infinity. And so now we have a result where the slogan I'd like to attach to it is no spin can misbehave, right? So if you go back to this picture, you see that I was, right, this is the ideal behavior. These were the oscillations in H space, and those we killed. Because if these oscillations have finite amplitude, then I take epsilon to be smaller than this amplitude, and there's a contradiction with the theorem we just proved, so these oscillations cannot happen. These gaps, in this version of the theorem, they can still happen because I still need to sum over all J. But in the version that we are about to present or about to write down is, I really have a limit as J goes to infinity. So for sufficiently large spins, everything falls into place. And these kind of games where you have infinitely many gaps also don't work. So, so it's really this kind of scenario that we're looking at. One hour, 2 minutes is what I'm timing. Can I say a few words about the modular bootstrap?
The questions, yeah.
Yes, so for the modular bootstrap, we have a nice result. What do I want to say? Let me think very fast. So let me say just the words. So we are looking at a modular lightcone bootstrap. Where I send now, instead of z bar to 1, we're sending tau bar to 1 in the modular invariant partition function, and we keep tau fixed. Tau bar to 0, of course. Then again, the cross-channel identity dominates, and we can say something about theories with C greater than 1, and a twist gap. And if you want to know examples about these theories, there are none really vigorously known, but you should go to Junshin's talk on Thursday for maybe an example of such a theory. And of course, we assume a unique normalizable vacuum, modular invariance, and so on. And then we basically say that, again, we have a strong result of this form. Here we already eliminated the reliance on Tauberian theorems because we just have an integral of the partition function that gives us the projection onto spin j. Then we have another integral with the test function, and we can just estimate these integrals. So we have a theorem that is, well, I'm not going to write it down because I'm out of time, but there's a limit as j goes to infinity. There's a test function, the h phi j of h. And then there is the OPE density. And we have a pretty good idea of what this limit is, or what it does. I mean, actually it diverges, so maybe, I guess I should write something like the tilde j to infinity. But that's a minor thing. And we have a good idea of that. And here we even did not need to use Vitali's theorem because the two channels, you can do an infinite integral over this, the equivalent of this theta variable, while keeping control of the dual channel expansion. But we did need to use modular invariance twice. So this integral, so the proof of this uses estimates of the integrand, and we don't just use the T channel expansion, we also use the S channel expansion again. But otherwise, it's really just estimating a double integral. So in that sense, it's just elementary stuff. No Tauberian theorems, no Vitali's theorem. You can give this to a second year math students, and all the manipulations will be perfectly understandable. So this, of course, allows us to bound the average gap. Right now we have a large J limit, really, so we can really say what happens for individual spin. We can show that the spectrum in these kind of theories must become dense for each spin individually. Well, for each spin, in the sense that people believe the spectrum to become dense, but maybe you had to average over J. So it's funny to think of a dense spectrum that arises by averaging. You can, for example, take an integer space spectrum for each J, and then for every J you have little offset, so that if you sum over everything, you get something that becomes gradually dense. That was one possibility that people had not excluded in the modular bootstrap, but now it's clearly excluded because for every spin, the average gap has to go to 0. And we have various other estimates and results that Pedro is already getting nervous, so that I will not talk about anymore. So thank you very much.
But we do have time for questions. We are not pressed. Yeah. So maybe Peter first, and then Kolja.
All right. Since I have the microphone, I'm going to. Sorry. What can you learn about the lightcone limit on the second sheet from all of this?
I think so the first thing is that there's a converse of this Tauberian theorem, which is an abelian theorem, which tells you that the lightcone limit on the second sheet is the same as on the first sheet, basically. So
in terms
it
of
is
how bounded it is.
Yeah, but it's dominated by the. So there's a slightly stronger result than what people know. Let's talk afterwards. So there's a literal statement at the very end of my paper, where I give a statement, but it's not. I can't write it down now. But it is not enough to prove these things like Lorentzian inversion formula and so on, because you kind of want to subtract the T-channel identity and look at the subleading terms. And that I cannot do. I just have a leading order limit statement.
Thanks.
So do I understand correctly? So the strongest version of your statement is when you increase spin to infinity, then the spectrum should accumulate around these lines.
The spectrum, when averaged against, right? This is, I want to make things precise. So when averaged, if you take J to infinity and you average a spectrum in H space with some test function.
Yeah, but it could be as small as you want, right?
Compactly supported, then it's going to be like GFF.
But say, how does it apply? Well, maybe I'm just missing something. To n equals 4, where we know the spectrum has log s term.
The spectrum of single trace operators.
Yes.
Yeah, but this includes the multi-twist, right? So I'm just saying, I'm making a statement about the double traces, because the single traces also decouple at large.
So your trace in context of n equals 4, this is only double trace and doesn't say anything about single traces.
No. I guess I'm making a statement about subleadingness of triple traces, because I say to leading order it's just a double trace.
Can I ask, are there simple, or are there multivariable generalizations of Vitali's theorem?
Possibly, I don't know. I think the whole subject of families of analytic function in more than one variable is complicated. Yeah, there's I tried to read some textbooks on this because I need it also for the flat space limit of QFT and ADS. But I didn't advance yet very far in the textbooks. Tom, one.
Can I? Yeah. So as someone who struggled in the past to make some aspects of this story rigorous with some modest success, I first want to just repeat that I think this is really amazing progress, and this still looks like magic to me, because this is much simpler than what we had to go through in our past work with Jashin and Sridip. And but I also want to emphasize something which I think is a crucial, I think, hint at what needs to be understood, potentially very interesting, is that, okay, in our work, the reason why we struggled to prove things that we managed to prove is that we were trying to reduce everything back to the CFT data encoded in values of correlation functions at some points. Like, okay, we had some estimates, and you may go through them, but in the end, all constants could be expressed, if you wish, in terms of correlation functions of CFT at some particular points. And so the reason why everything was so hard, because everything was also so explicit. And so here you have this magic Vitali's theorem, which allows you to do stuff like basically one-line proof, and but so far you did not manage to provide like a concrete degree of the rate for convergence. And so this may, okay, this is kind of, in my opinion, this may be also a feature, because this may mean that this rate of convergence, okay, you say, you know it's finite, but you don't know what it is. So this is this a new piece of CFT data, this rate of convergence? Could this be some new piece, some new characteristics of CFT which goes beyond like all other pieces of CFT data that we know and love? So this is, I think, an exciting thing to think about.
Yeah, thanks, first of all. And yes, I think there's something to be said about the rate of convergence, but of course we also have approximate physics level rigor estimates for the corrections that come from subleading terms in the T-channel expansion, but you want kind of the rate of convergence towards the prediction from the naive estimates. I think, yes, this Vitali's theorem is a bit magical, because it doesn't really say that much about what happens on the secondary sheets. It just says that it doesn't go wrong, and that's not a lot. So that's why the modular bootstrap result is stronger and nicer, because there we don't need Vitali's theorem, because we have two upper half planes where both, the upper half in tau and tau bar, where both direct and cross-channel decompositions converge. So here we need neither Tauberian nor Vitali's theorem. And here everything is explicit. And so here I'm pretty confident I can give you a prediction. It may be very weak, but I probably can give you a prediction for spin 25. What happens, and estimate it in terms of the value of the partition function and the twist gap and the central charge.
Last question by Tom, and then we should go.
So maybe you sort of answered this, but what are the prospects for including the second term, the anomalous dimension term? You've shown that the double twist operators exist, so now you include that term. What happens?
Yes, I think, right, there's a version of that question asked by Peter and now also by Slava that the control here is a little lost. So I have to think. I don't see an obvious way to take it into account, because after subtracting the leading term, you no longer have positivity. And then Vitali's theorem says that, right, the subleading term can still diverge, but it's, right, Vitali's theorem, you can't directly use Vitali's theorem, because the subleading term, given the expectation, it should be, right, smaller than the leading term by some power in lambda. But that is the expectation. But it's hard to prove, because all Vitali's theorem says it will never diverge as fast as the leading term. So it will be slower than the leading term, but it's not slow enough to actually say something something directly. So it's not so easy, I think. There's your challenge also. Vitali, sorry.
Let's thank Balt for a very nice talk. Go register if you arrived in the second week, and let's be back here sharp at 11:45. Okay. Welcome, everyone. Before we start, I have a few short announcements and one important announcement. So the short ones are related to food. So you have vouchers that you can use. And basically, each voucher is worth 20 reais, so it's like money, so don't lose it. There are 3 places you can go, which are on the website. And follow. Most people were here week 1, so they know how it works. So I'm not going to explain. Just ask someone that is going with you. When you should pay. When to pay thing can be a bit confusing. You don't pay in the beginning, you pay at the end. But ask someone that goes with you. Second announcement is that as people from the first week know, we have the talks in the morning here, and in the afternoon we can use everything in the other building. So it's a very nice building with sofas everywhere. You even have a rooftop with some chairs and so on. But they really insist that we have our name tags on because the building is open, and so they want to know that the people that are there are the people from the conference. So please don't forget your name tag. And last thing, so last week we tried with these parallel sessions, and we thought it was a big success. I mean, the rooms were full, so we want to do it again to give people more also, so that we can hear more people. And so we want to put one more parallel session this Friday. So we moved 2 of the speakers from this week to next week, so that we free up 2 slots. And those 2 slots, we will do 8 more parallel talks like in week 1. So all the 5 talks this afternoon, we already managed to find some people that are giving the talks, but if we didn't find you, you are knowing now, that all the 5 talks this afternoon are being moved to the parallel sessions, so that you will probably get a bigger audience like that, rather than the informal talks. And we still have 2 slots for Friday. So if you have volunteers, or if you want to volunteer someone, or if you want to present something, we still have 2 slots, come and tell us. And next week, the week 3, we'll probably do another parallel session, so that we give even more people more opportunities. So, and like I said about the building in front, it has 2 big seminar rooms that we can use for the parallel sessions, that people can also use for discussions and informal discussions and so on. But these informal talks, we are moving them to the parallel session. If you really insist to prefer to give an informal discussion in the afternoon, you can, but by default you are moved. So if you want to stay there because you want more time and so on, that's fine, but those informal talks in the afternoon, we don't assume people go. Whereas the parallel talks, we assume people go. And the parallel talks are also recorded and posted online and so on. So it's an upgrade, if you will. Okay, so with that said, one more thing. So speakers of this week, come talk to me at the end of this talk, because as you see, we have to shuffle you around a little bit. So, okay, so speakers of this week, come talk to me at the end of this talk. Okay, so now it's a pleasure to have Tom tell us about quantum gravity.
Okay, thank you very much. So I'm going to be talking about triangulations of quantum gravity in ADS-3. To sort of set the stage, let me go back a few years. I think that the discovery of controlled wormhole effects, higher topology contributions with multiple boundaries in the gravitational path integral over the last 5, 6, 7 years has required rethinking both the gravitational path integral and ADS-CFT more generally, with topology and complicated topologies playing a key role there. So pure gravity in 2 dimensions, that is JT gravity, is not dual to a particular 0+1 dimensional quantum mechanics. It's dual to an ensemble. It's dual to random matrix theory. So it's not quantum mechanics. And in 3 dimensions, it's very likely that a similar story is true. That is, what we expect in 3 dimensions is that pure gravity, meaning the theory that's as close as you can get to defining it just by integrating over metrics and summing over geometries. That pure gravity in ADS-3 seems to be dual not to a particular 2D conformal field theory, but to some sort of average over two-dimensional conformal field theories. This is similar to the random matrix story, but of course, in higher dimensions, there's a key ingredient, which is locality in the boundary directions. So in other words, when we try to define what we mean by a random conformal field theory, we need to impose the bootstrap conditions. And so the question is how you can define random or ensemble theories, including the constraints of the conformal bootstrap.
So it's probably my ignorance, but is the modern perspective not that the averaging comes from the semi-classical approximation on the gravity side? Is the Jan de Boer story, is that not where the averaging is coming from, or?
Well, in the general situation, say in more than 3 dimensions, then I think the semi-classical approximation is what leads to the averaging. But what's special about low-dimensional gravity, so 2-dimensional and 3-dimensional gravity, is that the semi-classical approximation is in some sense already a complete theory, because gravity is, we don't have problems with non-renormalizability. So when I say pure gravity, there's no such thing as pure gravity in 4 dimensions, but pure gravity in 2 and 3 dimensions is capturing the low energy sector of a UV complete theory, and that pure gravity, if you really want to have an equal sign, is going to literally be dual, we believe, to an average over CFTs.
Thank you.
So the set of, let's say, saddle point that will contribute in the pure gravity, is that there's still ambiguity? I mean, is that completely well defined?
Well, we don't know the answer to that in 3-dimensional gravity. I think what we have in 2 dimensions is pretty explicit, and we know how to do the sum over topologies. In 3D gravity, what we have is a bunch of examples that seem to make sense in various limits, but we don't know the full set of rules. It's almost certainly not a sum over saddle points. There are topologies that don't admit a saddle point that need to contribute to the path integral in order to get a sensible ensemble of CFTs.
Is it actually ruled out that you can have Liouville theory being due to some version of pure gravity?
Well, pure gravity has rotating black holes. So at least the pure gravity, in the way I'm thinking about it, is definitely not dual to Liouville. They're states with spin.
Well, maybe we can talk more later, but it's not obvious to me that it's a complete contradiction, because there can be an infinite factor that overwhelms that. Oh. Yeah.
Yeah, maybe we could talk about that after. I don't want to get stuck too much on discussing the ensemble, so other questions about what ensembles mean and everything, probably it's better if we discuss over lunch, because we've had those discussions in various iterations, I think, over the last few years, and will continue. What this story does is it takes the complexity of all the bootstrap conditions and translates that or maps that somehow in a way that we're still trying to understand to the complexity of all the different geometries and topologies that you need to sum over in the path integral of 3-dimensional gravity. And that, for example, different bootstrap constraints enter through the sum over topologies, and including different topologies in the path integral. Now, the mathematicians will tell you that when you want to organize the understanding of topologies and 3 manifolds, that the right way to think about it is by triangulating your 3 manifold into tetrahedra. And what I want to do in this talk is to develop a method for calculating the path integral in 3D gravity that's based on triangulations. And so this is a method that, when you take the semi-classical limit, will give back something like the way that mathematicians think about 3 manifolds, and will allow us to organize the individual topologies in a very convenient way. What I will not do, and we'd like to do in the future, is to understand how to do the sum over topologies, or how to do, well, mainly how to do the sum, or how to better formulate this CFT ensemble on the boundary. What I'm really talking about here is calculating gravitational path integrals on fixed topology. The goal, or the strategy, is to understand systematically how to calculate path integrals on very complicated topologies like this one. So let me explain what this is a picture of. This is a contribution to the statistics of OPE coefficients. So the easiest way to think about this duality is that gravity calculates for you the statistics of OP coefficients in the ensemble. So this is a three-dimensional, this is a three-manifold with 6 asymptotic ADS boundaries, 1, 2, 3, 4, 5, 6. So this is a contribution to the 6th moment of the OPE coefficients. Really, I should write all these out with different indices, and the indices are contracted in some way, but I don't want to write it. This would be a contribution from the path integral to that 6th moment of the OPE coefficients. The reason that this is calculating for you OPE coefficients is that what I've done here is I've inserted 3 heavy operators on each of these asymptotic ADS boundaries. So when you insert 3 heavy operators, what that does is and this was explained in papers of Pedro and collaborators, that when you insert heavy operators on the boundary, what that does is it effectively turns that sphere into a pair of pants, and then you can take this asymptotic boundary with heavy operators insertions and glue that to a pair of pants. So what's happening here is that we have this manifold in the middle that I'll call M, which is some complicated compact 3-manifold. These squiggles mean that there is some interesting topology in here. It's not just a topology that's drawn. So there's some complicated compact manifold with boundaries consisting of 2 Riemann surfaces, one of genus 2 and one of genus 3. And then each of those Riemann surfaces is decomposed into pairs of pants, and then each pair of pants is glued to an asymptotic ADS boundary. So the way we're going to organize calculating these statistics and doing the path integral is by chopping off the asymptotic regions, leaving this compact 3-manifold, and then further we're going to take the compact 3-manifold and decompose it into tetrahedra. The tetrahedra that we're going to use are what are called generalized tetrahedra. So let me write this. So the building blocks are generalized tetrahedra. So a generalized tetrahedron in 3 dimensions is, well, the simplest example is a truncated tetrahedron. So you can think about these topologically, or you can think about them as actual hyperbolic 3-manifolds, so on-shell solutions of Einstein gravity. The picture that I'm drawing here is on-shell. So let me explain what this is a picture of. This sphere is H3. So this is Euclidean ADS3. If I had drawn the tetrahedron inside of H3, that would just be an ordinary tetrahedron. But what you can do in H3 is there's a natural way of defining tetrahedra whose vertices are past the conformal boundary of hyperbolic space. So the way this is described is in embedding space. In embedding space, there's a natural way of thinking of the inside of this ball as being H3 and the outside of the ball as being 3-dimensional de Sitter space. And they're glued together on the conformal boundary. So this sphere is both the future conformal boundary in DS3 and the ordinary conformal boundary of ADS3. And then generalized tetrahedra are tetrahedra in this glued together space that's part de Sitter and part anti-de Sitter. What that allows you to do is to construct shapes that look like this. The defining feature of this geometry is that all of the faces of this polyhedron are geodesic hyperplanes, and also the truncated, how do I draw this? Let's see. All of the truncated faces meet their neighbors orthogonally. So these are right angles where the truncated faces hit. These are right angles, and what the reason that this will give us a good building block is that now you can take these polyhedra and you can glue them together in order to make smooth three manifolds. Okay, so that's the strategy. Let me restate it. So we're going to strip off the asymptotic regions, and then we're going to decompose this leftover three manifold into tetrahedra that look like this, glue them back together in order to form the three manifold. When you find solutions, hyperbolic three manifolds, solutions of 3D gravity that look like this, what you find are solutions, although I've drawn these boundaries as if they're smooth, but actually you get corners on each of these curves in the Pants decomposition. So I just can't draw that, but you should think of each of these boundaries as being what's called a pleated, so these are called pleated Riemann surfaces, and these are also what, this idea of three manifolds ending on pleated Riemann surfaces, this was introduced by Thurston and used very heavily in his work 40 some years ago on the proof of the hyperbolization theorem for three manifolds. So they're bent on these corners.
Tom, just a clarification. So these red lines are geodesics inside H3?
That's right. And what we're going to do is we're going to impose boundary conditions that fix either the lengths or the dihedral angles, the interior angles, on these geodesics. So in order to get into the details, here's the outline. I'm going to say a few more words about averaging, the averaging interpretation of ADS CFT, and how average CFT quantities are related to three manifolds. Then I'll review Virasoro TQFT, which is a topological theory that's used to calculate these things in 3D gravity. Then I'll get to the new approach, which starts with a topological theory called conformal Teraya-Vira theory, CTV. And then once we have this topological theory, we can use it to do this deconstruction of gravity into triangulations. And the main result that we're going to try to get to is a formula that expresses the OPE statistics of the ensemble of 2D CFTs in terms of something that's expressed in terms of the triangulation of a three manifold. So that's where we're headed. That's the goal. So let me start with a few words about ADS3 CFT2. So the simplest example of this correspondence between path integrals in 3 dimensions and OPE statistics is what's called the C0 wormhole. So the C0 wormhole is a 3-dimensional geometry that looks like this. It has 2 asymptotic ADS boundaries, and it has 3 particles going across. So these particles correspond to these particles correspond to operators in the dual CFT. So this is a contribution to C1, 2, 3, C1, 2, 3 average, and that's a on-shell geometry. You can calculate its on-shell action, and it gives this function C0, which depends only on the conformal weights. So C0 of H1, H2, H3, C0 of H1 bar, H2 bar, H3 bar. And this is the leading variance in this ensemble of CFTs. So this is interpreted as this variance in the ensemble. Now this is just the leading term. In principle, you're also supposed to include all the other more complicated topologies, maybe even off-shell topologies, and add up the path integral for all those contributions. This function C0 is a known function that comes from the Bootstrap. So C0 is related to the structure constants of the Liouville CFT, and it's sort of a famous function in Bootstrap and two-dimensional CFT because even in non-holographic theories, so just in complete generality, this function C0 controls the asymptotics of the OPE coefficients at very high energy. What's special about 3D gravity is that this is essentially the whole answer at leading order, not just at asymptotically high energies. It's not literally DOZZ. It has some factors of the Cardy density of states, but up to normalization, it's literally DOZZ. Yeah.
So, I mean, in some sense, gravity is a Chern-Simons theory. In other senses, it's not. But it raises the question: if you just take a compact Chern-Simons theory, what does this thing compute, and does it look like any average of OPE coefficients in the dual CFT or not?
By dual CFT, I guess you mean WZW model, maybe? Yeah.
Canonically associated CFT.
Right. I guess in that case, if you calculate. Yeah, I don't know what that gives. A key difference here is that in Chern-Simons, we don't usually sum over 3 manifolds. So I think that there's also, of course, a disconnected term. Which is just, looks like this, and there's nothing going across. And I think the obvious calculation that you would do in Chern-Simons would just give you this disconnected term. Now you could add a rule that you should include things like that. I'm not really sure what that's going to do.
Probably worth saying that it's a known result that you can apply Hamiltonian reduction to a WZW model and get a Liouville theory. And this reduction has been interpreted in terms of the Brown and Hanot boundary conditions in ADS3. So there's a way to also get DOZZ.
Okay, but I don't want to do complicated things. I was just asking what to do in the simple case of a compact Chern-Simons theory.
Should I regard this equation as a definition of average OP coefficient, or you have a separate definition? Because I can only see you can define the right-hand side by gravitational integral, but what about the left-hand side?
Good. The answer is that if you assume that the CFT is dominated by the identity block which we think is true in holographic theories, then you can derive this formula from the Bootstrap. And furthermore, without even making that assumption, the way to think about it is that we take this as input. So we calculate the variance. So we take this as input from the gravity side. And then the idea is that you take this input, you plug it into the Bootstrap equations, and it gives you the rest of the ensemble to all orders in some expansion. So there's a sense in which this is not really a check. It's more of a defining the ensemble. But then you take that and you plug it into the Bootstrap equations, and you have a check of every other observable that you calculate. So the next one I was going to mention is this c to the fourth, a connected contribution to c to the fourth. I won't write all the indices, but there's now 6 different states, there are 4 boundaries. This is a contribution to c to the 4th. And if you take this variance, then you can do a purely boundary bootstrap argument. You can show by a purely boundary bootstrap argument that there need to be connected contributions to the 4-point statistics, and you can match those between bulk and boundary. The bulk calculation, yeah, you can match those between bulk and boundary. Anytime you do these calculations, either in gravity or using Bootstrap, you always get all these factors of C0 everywhere. So the first thing I'm going to do is I'm going to normalize the OP coefficients by removing that factor. So I'll define the capitalCijk's to be the littleCijk's over the square root of this C0 squared. And with these normalized OP coefficients, then the statement is just thatCijk squared average is 1 to leading order in the topological expansion. What this does geometrically is it strips off these regions. Okay, so the asymptotic regions that are associated with the factors of C0. And if we talk about the statistics of the normalized OP coefficients, then we're just talking about the contribution of this sort of complicated interior region. For the case of the C0 wormhole, this one here, there is no interior region. You strip off everything, and you're left with a manifold that just sort of degenerate and flatten out. That gives you thisCijk squared equals 1. But when we get to more complicated topologies, it's useful to actually work with this normalization so that we're talking about the compact manifold in the middle.
So what does it mean to cut off the asymptotic region? Because I'm imagining some 3D gravitational path integral with some boundary conditions, and now you just move the boundary conditions somewhere else and you change them.
Yeah, we'll come to that in the last part. So how you cut it off depends on what boundary conditions you impose, but that'll be the topic of the gravity on compact spacetimes. Yeah. Okay, so next I want to review this Virasoro TQFT a little bit. First of all, this calculation is very doable just using direct metric formalism for 3D gravity. You write down the metric, you can write it down very explicitly, you plug it into the Einstein action and you calculate. If you just want the leading term, you can just do that calculation. Geometries like this are very difficult to calculate using the metric formalism, but fortunately this Virasoro TQFT was introduced as a way of doing these calculations in the bulk using something that's more like Chern-Simons language. And in Virasoro TQFT, you can do exact calculations in the bulk of geometries like this one. So Virasoro TQFT is a topological theory in 3 dimensions whose Hilbert space is the space of conformal blocks. Is spanned by the conformal blocks. So the amplitudes of Virasoro TQFT I'm going to write this way. So this is a path integral of Virasoro TQFT. The ingredients here are that gamma of p is a trivalent graph. where P is a tuple of conformal weights. So I'm using the Liouville parameterization of the conformal weights, where H is C minus 1 over 24 plus P squared. And then ME is a closed three manifold, the embedding manifold where your graph lives. So the way to think about this is that it's like Chern-Simons theory, where we work in a closed manifold and then we have some network of Wilson lines. The network of Wilson lines is this graph, and the Wilson lines are labeled by representations. In this case, they're labeled by the non-degenerate Virasoro modules with the states above the black hole threshold in 3D gravity, although this is all true at finite C. For this embedding manifold, you can take this to be a complicated manifold, but I am going to only talk about situations where this where these graphs you should think of as being embedded in S3. The final results are true also for more general manifolds. Yeah, that's right. So the ordinary boundary conditions in Chern-Simons will give you something more like WZW, but then just a few months after Witten's paper, like in 89 or so, Hermann Verlinde gave a different boundary condition where the space of states is the set of Liouville type conformal blocks. So in the Virasoro TQFT language, this C0 wormhole, this calculation, this was a picture of a 3 geometry. Now I'm drawing the same thing in Virasoro TQFT. It's a trivalent graph labeled by P1, P2, and P3. And then you think of that graph as being embedded in the 3 sphere. And this amplitude I have set equal to 1. That's a choice of normalization for the vertices. And that's the fact that the variance is 1 on the ensemble. One other example that I want to tell you is that if you look at the tetrahedron graph, so the tetrahedron graph has labels P1, P2, P3, P4, P5, P6. So the tetrahedron graph in Virasoro TQFT is the Virasoro 6J symbol, P1, P2, P3, P4, P5, P6. So this Virasoro 6J symbol is the crossing kernel for the 4-point conformal blocks. So this is the fusion kernel. Sometimes it's written this way: F, P3, P4, P3, P6, P1, P2, P4, P5. These are the same up to some normalization factors. And this is the expansion coefficient if you take a conformal block in the S channel and you expand it in the T channel, the Virasoro conformal block. Okay, so these Virasoro 6J symbols are the crossing kernels, is a crossing kernel of the Virasoro algebra. And there's one more diagram that's important. That's a diagram that looks like this. This one also gives you a crossing kernel. It gives you the modular S matrix, S hat, P1, P2, P3. So the two crossing kernels that you need to do crossing in 2D CFT are the crossing of the 4-point block on the sphere and the crossing of the 1-point block on the torus. And these two diagrams give you those crossing kernels. All other Virasoro TQFT amplitudes can be evaluated by some simple diagrammatic rules. So if I give you an arbitrary graph, you can very readily evaluate the diagram using these rules, and the answers you get will always be some integrals of products of these crossing kernels, the 6J and the modular S. So Virasoro TQFT has two uses. One is that this is a very efficient way of thinking about the properties of conformal blocks and the properties of the Virasoro crossing kernels and how conformal blocks behave under crossing. Because what this TQFT is doing is it's recasting Virasoro conformal blocks as the states in a quantum theory. And then if you want to know, for example, what a conformal block in one channel looks like in another channel, you just have to calculate some inner product in that TQFT. So that's what Virasoro TQFT is doing for you. In our setting, the other thing it's doing for you is that it's allowing you to calculate exactly gravitational path integrals on complicated geometries like this one without having to ever find the metric. This is both a good thing and a bad thing, I suppose, because on the one hand, you can get the exact answer for a geometry like this one, but on the other hand, using Virasoro TQFT, you can't describe what this manifold actually looks like. Even once you take the operators to be heavy, it's even a sort of complicated question what the topology of this manifold is. If the operators are light, just like particles, then it's obvious what the topology is. It's exactly what I've drawn here. But when you take the operators heavy over the black hole threshold, then it changes the topology. It's not literally the topology that's drawn here. So now I'll move to the new approach, which is based on this conformal Tauberian theory. So CTV is a dual formulation of this Virasoro TQFT that instead of, that is based on triangulations. So you should think of Virasoro TQFT as being a Chern-Simonsy way of doing these calculations, and then you should think of CTV as being a method that's based on triangulations that's much closer to the metric formalism. So you should think of that, think of Virasoro TQFT as like the Chern-Simons formalism, and CTV as like the metric formalism, but it's a formalism that'll give us exact amplitudes. So the starting point of CTV is to triangulate. Let me find another marker. The starting point is to triangulate, that is, with tetrahedra, your Virasoro TQFT graph. So you have some trivalent graph embedded in a 3-manifold, and you're going to triangulate that with tetrahedra. And you're going to choose the triangulation in a way that it includes the graph as part of the triangulation. There are two types of edges in this triangulation. There are external edges, which belong to the original graph. Those are labeled by conformal weights P. And there are internal edges, which do not belong to the original graph. And I will label those by conformal weights P tilde. So we have some triangulation with all the edges in the triangulation labeled by conformal weights that includes the original graph as some subset of edges in the triangulation. Then the definition of this theory So the partition function of this theory for a graph gamma embedded in a three-manifold ME is the integral from 0 to infinity over all of the internal weights, the p tildes, weighted by the Cardy density of states. So this is Cardy, rho 0. And then the integrand is defined by the triangulation. So we take a product of all the tetrahedra over all the tetrahedra delta in the triangulation, and then there's a weight factor associated to each tetrahedron. The definition of this weight factor, W, yep. So if you have a tetrahedron with weights P1, P2, P3, P4, P5, P6, then the weight factor is the Virasoro 6J symbol, P4, P5, P6, P1, P2, P3. So again, the building block of this theory is again the fusion kernel of the 4-point Virasoro block. Something important to note that I'll come back in a minute is that the rows are swapped here. In Virasoro TQFT, when you see a tetrahedron, it's P1, P2, P3, P4, 5, 6 in the second row, and in CTV, the rows have been swapped. So just note that, and we'll come back to it in a minute. So this definition of CTV, so there's a theory, there's a topological theory called Tauberian theory, which is defined in the same way for ordinary TQFTs up to a normalization factor. So in an ordinary TQFT, the spectrum is discrete and the total number of states is finite. The difference in CTV is that the spectrum is continuous and the total number of states is the integral dp of the Cardy density, which is infinite. Okay, so there are many of the results in Tauberian theory rely essentially on the fact that the number of states is finite. So this is going to be a key difference. What it means is that there are many results in Tauberian theory that carry over, and there are many results that do not carry over. And so our task is basically going to be to understand what are the results from Tauberian theory that can still be applied in the case of the Virasoro 6J symbol and this infinite number of states. One of the consequences of this is that, well, this is just the definition of the partition function, but I haven't, an essential thing here is showing that this is well defined. So on the right-hand side, I've chosen a triangulation of the three-manifold, but the amplitude that we're calculating is not allowed to depend on that triangulation. So the difficult part, or the non-trivial part of trying to define this theory, is understanding whether this integral is finite and whether it's independent of the triangulation. For this to make any sense, you need the right-hand side to be independent of the triangulation. One consequence of having an infinite number of states is that only certain triangulations are allowed. So the conjecture supported by examples is that this is well defined on what are called large triangulations. So large triangulations are triangulations that have no trivial interior vertices. So let me try to draw a picture to explain what it means for a triangulation to be large. If you have a tetrahedron in your triangulation, then you are not allowed to decompose that into smaller tetrahedra. So something that you could do in ordinary theory of triangulations or Triangulating theory, something you could do is you could put a point here in the sort of centroid of this tetrahedron, and then you could decompose it into 4 smaller tetrahedron by cutting it up this way. You're not allowed to do this in CTV. If you try to calculate amplitudes that involve any kind of vertices, any kind of interior vertices that look like this one, then you get divergences. So we're restricted to certain kinds of triangulations. Which Z? Yeah, I think the topology there is not obvious.
But it's something like, you want to say, it is supposed to be kind of around a saddle, which is kind of like a S3 with this skeleton of this graph kind of cut out and replaced by like the appropriate boundary, but then you have some PVC black holes in the middle.
Yeah, that's essentially, yeah, that's right. So the topology, yeah, if the states are heavy, then you should take this graph, embed it in S3, and delete a regular neighborhood of the graph, and that's the manifold in which gravity lives. Well, if the graph is connected, it only has one boundary. But you can have disconnected graphs. Now, if the graphs are separable, then that diverges due to the infinite number of states. But if you have disconnected graphs that are knotted with each other, then you can have multiple boundaries. And like this example I drew in the beginning, this crazy looking example I drew in the beginning, that would correspond to 2 knotted graphs. So the main result in CTV that I want to state is the relationship between this derived Viro-type theory and Virasoro TQFT. So here's the formula. ZCTV for an arbitrary graph in a general 3 manifold in situations where this is well defined is the modular S transform of Virasoro TQFT. So let's write that. Integral, let me put a prime here, so we'll call ZCTV of P prime. So we integrate over all the weights, product I equals 1 to n, S pi prime pi, Z vir, me gamma of p mod squared. So this is the Virasoro TQFT amplitude squared. The fact that it's squared, this is related to the fact that CTV is like gravity, and gravity has 2 copies of an SL2R type Chern-Simons theory. So this is squared. The only new ingredient here is this modular S kernel. So this is defined. This is the usual S transformation. S p prime p is 2 root 2 cosine 4 pi p prime p. So I'm writing it as an S transform, but it's just a Fourier transform. So these 2 theories are related by a Fourier transform. The proof of this identity is non-trivial. It's an identity that's also true in ordinary discrete TQFTs. And so it's a known, in the context of discrete TQFTs with a finite number of states, this is a known result. And the non-trivial thing here is just to redo the proofs in a way that never uses the finite number of states. Okay, so it turns out that you can do that. And this formula is therefore also true in CTV. I will not try to explain the proof. There's a diagrammatic proof, but it's sort of long. But I'll just briefly say, well, let me not try to draw any pictures, but I'll just say in words that the relationship between these theories is a geometric, you're dualizing the tetrahedra. So when you triangulate a three-manifold into tetrahedra, there are two ways to describe it. You can describe it using the edges of the triangulation, or you can describe it using what's called the dual spine. The dual spine of the triangulation is the graph that goes where that replaces faces by edges. So there's a dual graph, and there's this graphical relationship sort of translates between the two sides of this equation.
Tom, sorry, just to go back to gravity, so the claim is that also if you do the path integral in gravity order by order in a large C expansion, you get that ZCTV? Is that the statement?
With the appropriate boundary conditions, which I'll come to in a minute, with fixed angle boundary conditions, you get ZCTV. Yeah.
And this is a statement you can do, I mean, a few orders, or is there a way to argue to all orders in 1/C? What is the status of that?
Yeah, it's not proven, and you can't do the gravity calculation to all orders. I would say that this is so the argument for this is a set of consistency checks. The way the argument goes, I'll describe it in a second, but the way the argument goes is that first you study the fixed length path integral and relate that to Virasor TQ of t, and then you find that this transformation from fixed length, this S transformation, is a change of boundary condition in the gravitational path integral from fixing the lengths to fixing the angles.
This may be a naive question, but how about states with like, here we're talking always above the BTZ threshold.
Yeah.
How about states with like with the conformal dimension that would be lower? Is this because if it's some kind of semi-classical expansion, so this wouldn't appear at that point, or? Like we're always integrating from 0 to infinity p, but we would have imaginary p
well,
in that case.
So on the right-hand side, the only thing that's appearing here is states above the black hole threshold. But you can take this formula, evaluate it, and then analytically continue in p prime. And so there is some corresponding formula that also works for states that are below the black hole threshold. But then you have to be careful about making sure that you did the analytic continuation and included all the extra poles and everything there.
Thanks.
So the last thing I want to describe is how this is related to doing gravity on a compact three-manifold. So usually we do ADS gravity with asymptotic boundaries, but as I described at the beginning, we're going to chop off all these C0 asymptotic factors and just impose some boundary conditions on a finite boundary. The kind of path, so if you do something too simple, this just won't work. Okay, so if I say I want to study gravity on a genus 2 handle body with some boundary conditions at finite distance on the boundary of this handle body, if I impose some simple boundary conditions, then what's likely to happen is that there won't be a saddle. But if you choose a topology of your three-manifold that's complicated enough, or you choose boundary conditions that are complicated enough, then you can find solutions. So what we're going to do is we're going to fix the length or the angles on a set of curves, the simplest example I know of that gives you a saddle point is one where you fix lengths on the following cycles. So 2 obvious cycles, and then you have to pick a sort of complicated looking last cycle that looks something like this. Okay, so there are 3 closed curves that I just drew. Probably it's hard to see now, but I only drew 3 curves. And if we impose lengths L1, L2, and L3 on those curves, then there's a solution of 3D gravity. There's a hyperbolic 3-manifold of finite volume that satisfies those boundary conditions for an appropriate choice of lengths. If we fix the lengths, if we fix the angles, then we get an amplitude I'll call ZA. So the fixed angle amplitude is ZA. Or we can fix the lengths of those curves, and I'll call that ZL. I'm going to parameterize lengths and angles by P, the Liouville momentum, so that we can compare. And the change of the parameterization here is that angles are given by 2 pi I BP, and lengths are given by 4 pi BP, where B is the usual Liouville B. Just think of this as the semi-classical limit. This is like related to this is related to the central charge. It goes to 0 as the central charge goes to infinity. The lengths of these curves are conjugate to the angles, and so the relationship between these 2 path integrals is ZA of M gamma P prime is equal to integral dNP product of S P prime P ZL of M gamma P.
Sorry, Tom, did you define the angle? Sorry, maybe I missed it.
By the angles, I mean so you're looking for solutions that have corners on these curves, which I'll draw locally like this.
You mean the curves are the red curves, the geodesics?
It's the red curves, that's right. And the angles mean the dihedral angles where these 2 surfaces meet. So there's an interior angle at each of these boundary curves, and you can impose boundary conditions that fix those angles.
So these manifolds are not smooth?
The 3-manifold is smooth, and its boundary is smooth, but the embedding of the boundary into the bulk has delta functions in its extrinsic curvature. So the intrinsic geometry of this 3-manifold is perfectly smooth, but its boundary is embedded with corners.
Where is the boundary? I'm missing it.
Yeah. This is filled in. So
Okay.
this thing is filled in, and the boundary is this genus 2 surface.
I should think of it like that. Yeah.
And when you find a solution, it'll have corners.
And the curves are on the boundary? Or
The curves are on the
inside?
boundary, correct. And the corners are on the curves.
So I would expect, I mean, if you have some 3-manifold and you specify some boundary conditions, I would expect you to have to specify the moduli of the Riemann surface, plus perhaps some additional information.
Plus some what?
Plus perhaps some additional information related to this fact that you have these strange boundary conditions with these corners, right? So don't the moduli of the Riemann surfaces enter somewhere also?
So the boundary, you can think of the boundary conditions as specifying a point in Teichmuller space for this genus 2 surface.
Yeah.
And
That's
for
it?
a point in Teichmuller space is specified by 3 complex lengths. I'm talking about the case only with real lengths. So this is some real slice of Teichmuller space. And so there's 3 real numbers that specify the boundary conditions.
So it's really just a parameterization of the Teichmuller space?
Correct.
Ah, okay.
Correct. Well, with lengths, that's right. With angles, you should just think of it as the conjugate of that. the phase space is, so the phase space is the cotangent bundle of Teichmuller space. So you can either specify a point in Teichmuller space, or you can specify the dual momenta, which are the angles.
Tom, I didn't understand how the boundary condition is defined from the gravity path integral point of view. Can you explain that?
Sure. Let me start with the fixed angle one. So with the fixed angle one, one just takes the ordinary gravity action. So this is the Einstein-Hilbert term and the GHY term, and then add to it a term like this, which is a term that's integrated over the curves where you want to specify the boundary condition. And so what this does is it sort of adds a defect particle that lives on the boundary. And if you now go through and derive the equations of motion for this action, you'll find that there's a boundary equation. So now you vary the action and everything, and you'll find that there's a boundary equation of motion that fixes the extrinsic curvature in such a way that you get a corner of angle psi.
Well, what about the part of the boundary away from the curves?
There it's just free. It's Neumann.
It's Neumann.
So it's Neumann, so yeah, I should have said that. So it's Neumann boundary conditions away from the curves, and then you fix either the length or the angle at the curve. So these will end up being geodesic hyperplanes attached on folds, like a polyhedron. Time is up. It's flashing. I'm going to write my final equation. So the exact So the final result is how all these things are related to each other. So the statement is that the exact path integral with fixed length boundary conditions is equal to the Virasoro TQFT amplitude mod squared, and the fixed angle path integral, well, now the fixed angle path integral is related by this Fourier transform, but we know that Virasoro TQFT and the conformal Taraya-Vira theory are also related by a Fourier transform. So it follows that the fixed angle path integral is just identical to Taraya-Vira theory. To sort of unpack this a little bit, what this means is that, so OP statistics are naturally expressed in terms of Virasoro TQFT, but now you can write those OP, but this is related by this change of boundary condition to conformal Taraya-Vira, and so by putting these two facts together, you get formulas for the OP statistics given in terms of triangulations. That's what we were going for, and that's where we are now. So I had an example that I was going to draw that would be helpful, but maybe I should stop, and if people want to ask me about the examples, we can talk about, I can draw one more picture of an example, but let me just in words mention a couple of open questions. So first of all, I didn't address, this was all at fixed topology. I didn't address the problem of summing over topologies. I think that's one of the very important open questions. It didn't address how to define the ensemble in the boundary language. I think that's the other really big important open problem here, I believe. I think it might help for both of those, because now the CTV theory is essentially the metric formalism. It's an exact theory that's defined topologically, but once you calculate amplitudes in CTV, each tetrahedron, you can calculate each tetrahedron individually, and the 6J symbol is just the on-shell action for that tetrahedron. So when you express things this way, you're just summing up the on-shell action for a bunch of tetrahedron in your 3 manifold. One other thing I want to mention is that, so a lot of these results that I'm borrowing from on ordinary TQFT, so these actually were also interpreted in terms of quantum gravity by the community studying the spin foams and spin networks, okay? And in fact, some of these relationships, like the relationship between Teraya-Viro and the Chern-Simons type formalism, there's a formula like this that was already interpreted in terms of 3D gravity, but it was 3D gravity in de Sitter space. When they were studying this problem, they had a finite number of states, which doesn't make sense in anti-de Sitter, but it does make sense in de Sitter. They also had what we would call an imaginary central charge. Again, that doesn't make sense in ordinary ADS-CFT, but that's exactly what you need in order to try to formulate a theory like this in three-dimensional de Sitter. So there's some interesting connection here to de Sitter that I think is really worth revisiting. But I'm out of time, so let me stop here and we can do questions.
Questions? Well, let me ask one naive one before. So, say in 2D, when we study Yang-Mills, we say it's a bit boring and topological, and then we couple fermions, for example, and we get something interesting, like the 't Hooft model and so on. Can we couple something to this 3D gravity, the minimal thing, just to give it a little bit more meat?
Well, one answer is that we could couple these defect particles, and that's sort of what we did in the paper 3 years ago, was adding the defect particles. But I'm not sure that we really need to, because gravity already has black holes in it. So it's true that on a fixed topology, it's sort of boring and topological, but once you start summing over topologies, it does have lots of states and everything. So I'm not sure that you really need to add the defect particles. But it would be nice to try to add matter. I think what's going to happen if you add matter is that then you'll really have to be talking about the low energy effective theory. Once you start adding matter to 3D gravity, it's not renormalizable anymore. You get divergences on short cycles. Maybe then you can phrase some ensemble duality for the effective theory, but I doubt you'll have an exact or all orders statement where that theory is dual to an ensemble.
Tom, I'm a bit confused with the logic here. So first thing is, what do you mean by this word exact that I asked you before, and not sure what you mean by the word exact path integral in this sentence?
So this is the gravitational path integral on a fixed topology 3-manifold with either fixed length or fixed angle boundary conditions. But it's exact to all orders in perturbation theory on that topology.
So then I misunderstood. Before you said that you could check some orders, but now you're saying that you know how to do it to all orders in 1/C.
I would say, so this formula is a proposal with lots of evidence, and that's the sense in which you can't check it to all orders. Okay. And then if you believe this formula, this one follows by doing the Fourier transform.
Yeah, and then about the logic, I guess you mentioned, but okay, we can do this gravitational computation in principle to some orders, and now you have a formula that you conjecture is the right one to all orders. And then you say that's some average of ensemble of CFTs, and you almost didn't say anything about that. So what is this ensemble? What can you give a bit more of the context of what should I think about it?
Sure. Yeah, I didn't talk about that because I don't really have anything new to say about it, but I can say old things about it. Okay, so the way we described this in the paper in 2022 was that it's an ensemble of CFT data. You have some scaling dimensions and OP coefficients, and you don't try to say anything except what are the statistics of those scaling dimensions and OP coefficients. So it's an ensemble. The minimal form is that I just tell you what answer you get when you put a bar over a bunch of CIJKs. So that's the minimal definition of the ensemble. What we would like is something more microscopic than that, something that's more like random matrix theory in 0+1 dimensions. There's been various explorations of this. So there's the tensor network approach of Sonner and Jaffers and collaborators. where you essentially take crossing and you use it to define a random matrix type theory. There's another approach of Eric Perlmutter and collaborators that works in melon space, and I think they have some really interesting proposal for what the answer should be, but it's not really been, it's a proposal that seems to make sense, but whether it's exactly the same as gravity is not yet known. I think we don't know the answer, though. We don't know what that ensemble is supposed to look like as a microscopic theory. What I would like to have is something more like a random Hamiltonian. That's what we have in 0+1 dimensions. Of course, if you're going to do that in 1+1, then you have to make sure that your Hamiltonian is local. But there are ways of writing down random local Hamiltonians. And maybe something like that could define the ensemble.
Any other questions? If not, let's thank Tom. And the speakers of this week, please come to the front. Or, yeah, come to me.